Hello, everyone.
Hey, Martin.
Hello.
John, I see that there are still attendees that are joining. Maybe
Okay.
we can wait another minute and then I'll.
Sure. I'm happy to completely defer to you on the timing.
Okay, wonderful. Okay, maybe I'll get started. Hello, everyone, and welcome to our seminar today. I'm delighted to introduce our speaker, John Kleinberg. John is the Tisch University professor in the departments of Computer Science and Information Science at Cornell University. His research focuses on the interaction of algorithms and networks, the roles they play in large-scale social and information systems, and their broader societal implications. He's an extremely well-accomplished scholar. He's a member of the National Academy of Sciences and the National Academy of Engineering, and the recipient of MacArthur, Packard, Simons, Sloan, Vannevar Bush Research Fellowships, as well as awards including the Harvey Prize, the Nevanlinna Prize, and the ACM Prize in Computing. So today, John will tell us about his work on fairness and bias in algorithmic decision-making. And before I turn it over to John, let me make a quick announcement for the audience. If you have quick clarification questions during the talk, please utilize the chat window. We'll try to bring some of these questions to John's attention during the talk. And if you have longer discussion questions, please save them for the Q&A at the end of the talk. During the Q&A, we are going to unmute you so that you can ask your questions directly to John. John, thank you for taking the time to join us today. So I'll stop sharing my screen so that you can share yours.
Sounds great. I will share my screen here. Do people see that?
Yes.
Is that working? Wonderful. Well, thanks very much for the invitation to take part in this seminar series. It's a pleasure to be here, and I look forward to getting to discuss this with you, and look forward to any questions you might have. What I wanted to talk about today was some research theme that has gained an increasing amount of momentum over the past 5 to 10 years, focusing on the use of algorithms for decision making and the ways in which issues of bias can creep into algorithmic decision making. This is a topic which has drawn attention from a number of different research communities, and in keeping with that, the work I'll be talking about here is joint with a number of colleagues from different areas and disciplines. So my PhD student, Manish Raghavan, and then 3 faculty in 3 different areas, Jens Ludwig at University of Chicago in public policy, Senthil Mullainathan, also at Chicago Booth in behavioral economics, and Cass Sunstein, professor of law at Harvard. I want to, in this sort of talk, partly what I'll be talking about is motivated by the particular role of algorithms, partly about the nature of providing mathematical models for biased decision-making more generally, and really thinking about where those 2 things interact with each other. By thinking about bias, we can learn about the role algorithms play. And in a way, the converse is perhaps sort of also true, and perhaps a little more counterintuitive, that by thinking about how algorithms have entered the system, the kinds of formalisms that we develop potentially shed light on some human decisions as well. So with that in mind, I wanted to sort of talk about the starting point for this work, and in a sense, the starting point for this line of research in general over the past few years, was this realization that some of the kinds of decisions that we've gotten very good at making in the online world, based on predictions trained on a large amount of data, potentially have analogs in the offline world. And so the question comes up, should we be thinking about the use of algorithms there too, and what would that look like? So here's an example of a decision that we've gotten very good at making in the online world, ranking and recommendation. So this is a screenshot from a Netflix help page where they explain how they make predictions about the probability that you're going to like a particular movie. And they follow what you might call the standard machine learning pipeline, in which I take an individual, I map them to a collection of features, I pass that through some decision-making entity like an algorithm to optimize some objective function, like the probability that you're going to like this movie. Okay. And people asked themselves, if we've gotten very good at making these kinds of predictions, let's think about places in the offline world where some similar kind of activity seems to be happening, right? So at some level, we could think about the process of applying for a job as having some similar components. I take an individual with their complex past work experience. I reduce that to a tabular representation like a resume. That gets handed to a typically human hiring committee that looks at the resume and then makes a decision, right? And here, of course, as all of you know, both from empirical work on this as well as your own personal experience you may have had with hiring, that it's unclear what the objective function actually is here, right? It's unclear exactly what prediction is being made, but we feel that some decision is being made. Possibly a prediction of whether they'll be a good employee. It seems hard to formalize. We'll come back to that point. But similar things happen with, for example, college admissions. We take someone's early educational experience, their high school experience, reduce all of that and their other interests to a tabular form like a college application. It gets passed to, again, a human decision-making body that, again, has a kind of complex, unclear objective function. And so all of these are what you might call screening decisions, right? The decision to hire someone, the decision to engage in admissions, decisions on credit and lending, will someone successfully repay a loan? We even see this in the realm of criminal justice, where at a pretrial detention hearing, the law, strictly speaking, is asking the judge to make a prediction, to predict whether the defendant will return for their court appearance without committing the crime in the meantime. And so the question is, if algorithms are good at making predictions, if these involve a component of prediction, what role might algorithms be able to play? And in particular, what role might this decision-making, this machine learning pipeline play, right? Which we recognize from both human and algorithmic decisions, where individuals get mapped to some kind of essential features, passed through a decision-making entity, leading to some prediction. Now, all of these are what people have increasingly come to call high-stakes domains, because each decision matters a great deal to somebody, right? It matters a lot whether this person gets hired for a job, whether they get into college, certainly whether they wait for trial in jail or in the community. And we might distinguish that from, say, the Netflix example, where it doesn't really matter if it was correct that you like this movie. It doesn't really matter whether Facebook showed you this news article or that news article. I should say that high stakes here versus low stakes is a question of the granularity of the decisions. It's clear that we take something like which news article you saw this morning on Facebook, which doesn't ultimately really matter. We take 100 billion of those, and in aggregate, it adds up to something extremely high stakes, like the formation of public opinion in a country as an election looms. So the online world and the offline world both have these increasingly high stakes that algorithms play a role in. I think my distinction here is more that in these offline domains, each individual decision by itself matters a lot to somebody. Whereas in the online world, we might need to aggregate many of these decisions. For all these reasons, in these kinds of decisions, as people begin to use algorithms, people ask the question, what is the potential for bias to come into the system? And in order to think about the potential for bias in algorithms, we should sort of think about it in two other aspects. One, bias in human decision-making, since that's ultimately where the algorithmic bias is going to come from. And second, just the mathematical modeling of bias decisions more generally, which ultimately is going to be the topic of my talk, more broadly than either human or algorithmic decision-making. So there's a huge amount of empirical work on bias in human decision-making, both explicit bias as well as implicit bias, when somebody is trying to control for their bias, but potentially is not able to do that successfully. And these empirical studies have established some troubling regularities in the way we engage as people in screening decisions. So, just to pick one of many canonical examples from the explosion of literature, empirical literature on this in the 1990s, this plot on the right is from an influential paper by the two Swedish social scientists, Christine Venevas and Agnes Wold, and published in Nature in 1997. And just to kind of walk through it, because it gives a sense of what I mean by bias in screening decisions. What they did was they looked at data from many years of evaluation of European Research Commission grant proposals. So you submit a grant proposal, it gets evaluated by reviewers. One of the fields in the evaluation is to assign what was then a so-called competence score to the principal investigator. How competent is this person to do the proposed research? And what Van Rost and Vold did was to ask, how well do these competence scores line up with external measures of impact, right? And so the question, of course, how we define that. And so they tried many, many different ways of doing this. Number of papers in high-profile venues, citations to those papers, number of past funded awards, success on those awards, and so forth, and many different ways. And for all the different ways that they attempted to do this, they found the following robust phenomenon, which is we see in many other studies of this type, that for a fixed level of their measure of external impact on the x-axis, we look at competence score on the y-axis, we see that for a given aggregate bin of total impact, men are consistently scoring higher on competence score than women. Or if we read the plot horizontally, to achieve the same competence score, women had to have enormously higher amounts of external impact. Okay, right. A finding that is sort of has been unfortunately recurring, as people continue engaging in studies. So, and again, this is about an aggregate effect, right? It's the attribution problem here is challenging, right? Where is the bias happening? Who's responsible for it? Are they consciously aware of it? All of these are challenging questions, right? It's not clear that any one person or group of people got together and planned to engage in this, but rather it's some sort of an emergent effect of the system that's doing this evaluation, and it's causing this pernicious disparity that's going on. Okay, so that's a sort of snapshot of human bias, which I'll come back to. Algorithms kind of make this picture interesting because algorithms, in contrast, have no direct incentive to exhibit bias. That's essentially almost a self-referential statement. Algorithms operate on some feature vector of numbers. They have no a priori knowledge of what these numbers mean. They're simply trying to optimize some loss function. Despite this, there are many sources of potential bias in algorithms. And we sort of see from the previous slide how that might happen. Suppose, for example, you were building an algorithm that was supposed to be evaluating European Research Commission grant proposals. And you said, I want to keep subjective human judgment out of this as much as possible. I'm going to train this algorithm simply on administrative data based on the funding of past proposals. But in this administrative data would be a field called the competence score, which, as we see on the previous slide, contains the bias that was already present in the human decision making. And so once that's in there as a label, the bias makes its way in. Or conversely, perhaps I'm trying to replace evaluators by training the algorithm to predict competence scores. But it's not clear that's actually the measure I want to predict, given the problems that we see with it on the previous slide. So all of these are the concerns that we might have in using algorithms for decision making. Notice also there's this interesting connection here between the issue of bias in algorithms and the issue of being able to interpret or audit the process by which they are constructed. Because if we're going to look for evidence of bias, then we want to know something about how the algorithm was constructed, what data was used, what objective function was used. And this essentially was sort of the starting point for some of the work that Jens, Sendel, Cass, and I were doing. That if we think about fundamentals of the issue of auditing bias or detecting discrimination or challenging discrimination is the attribution problem. We need to figure out where it happens so that we can try to remediate. With humans, that's extremely hard because of the opacity of human decision-making. Algorithms don't just change things quantitatively. It's not just that they can handle more data, make more decisions more rapidly. They've changed something qualitatively, that suddenly the notion of, for example, the objective function, in a sense becomes knowable, right? There's a sense in which, complicated though the Netflix recommendation function, the new Facebook newsfeed ranking function might be, it is written down, it is explicit. We can probe it, we can pass synthetic instances to it, we can treat it like a natural system and do experiments on it in a way that we can't really with human beings, right? If you've been on a human hiring committee, then you know that at some level you can try very hard to write down your objectives, you can write down criteria, you can agree on them, but in the end, you're not hand simulating an algorithm. You are doing something that has a certain unknowable component to it. That's just a fact about human decision making. Okay, so with this as the context, I want to talk about two kind of more technical snapshots of places where we might try to model bias in decision making, and in the process, learn about how this bias operates. And I'm going to try to do this at 2 levels of abstraction. So in the first part, I'll take the bias essentially as given. There's a decision-making entity, and it won't really matter in this part of the modeling whether it's a human or an algorithm or something else. It's going to be trying to rank. So all of my stories are going to be about ranking applicants, ranking job applicants, PhD applicants, what have you. This decision maker is going to be trying to rank, but they have a bias that essentially causes them to make systematic errors on a certain group. And we're going to look at the effect of that, but we're not going to ask where those errors are coming from. That's going to be the first part. Then I'm going to actually talk about how the actual implementation of the decision rule can lead to dangers of bias in itself. Okay, and this is the part where it will matter if we're talking about a human or an algorithm. And the second part will become more explicitly algorithmic. Okay, we'll take a simple model of the actual mechanics by which decisions get made from feature vectors, and we'll say as we begin to modify the decision rule or simplify the decision rule, can we actually see at the implementation level how bias begins to come? Okay, so for this first part, I want to stay at this high level and talk about just abstract decisions with a kind of abstract notion of bias that simply shifts the evaluation systematically for a certain group. Now, so the context might be the following. Let's say I have a set of applicants, and I'd like to choose a short list of K, right? So maybe this is a group that I would like to invite for interviews. Maybe I'm going to give these K people an award. I'm going to put them on a review committee or an advisory committee, something like this, okay? But these K people are going to receive some kind of accolade. And the concern is that there are 2 groups, let's call them X and Y, and we're concerned about bias against X candidates, okay, in some very abstract sense. So one intervention, so the situation I'm describing here, obviously we see in the world, right? We have shortlists, we have evaluation, we have groups, and we're concerned about disparate impact. One intervention that's become increasingly popular is this thing called the Rooney Rule. Many of you, if you've engaged in hiring or giving out of awards or assembling of panels, you may have encountered this. It says, essentially, we're going to commit to include at least 1 X candidate on the shortlist, right? We're concerned about bias against X candidates. So we're going to say, I will not choose a list of K that's entirely from group Y. The Rooney Rule is named after Dan Rooney, who in 2002 was the owner of the Pittsburgh Steelers in the National Football League. And he chaired a committee of NFL owners, which was facing its sort of profound lack of diversity in head coaching positions. Its head coaches were almost entirely white. It was admittedly also facing a looming class action lawsuit. And they essentially decided that they were going to agree to this rule. They're going to enforce it on themselves, that in the future, whenever they go to hire a head coach, the set of candidates they interview, they promise, will include at least 1 minority candidate. Okay. This is then something that began to spread throughout many sectors of the labor market. So in 2015, then President Barack Obama exhorted the tech industry to use this for executive hiring at tech companies. It's been used for composition of boards of directors. We see it in many places. You yourself may have encountered it in some selection process you've been involved with. When people have done legal analysis of it, people like the Rooney Rule because it seems to thread this sort of narrow path between things that would be too weak to be effective and things that would be so strong as to be legally challengeable. And so it's been a very simple, lightweight heuristic that people have used. Despite the simple statement, as I'll try to argue in the next few slides, it actually induces a relatively complex dynamics in the decision. It's sort of surprising that something this simple could lead to sort of complexity, but we'll see that it does. So there's been a bunch of empirical work on the Rooney Rule, including in its original formulation in the National Football League, where at the moment the Rooney Rule began, some nice retrospective work by Cynthia Dubois in 2016 showed that, in fact, the minority representation in NFL head coaching positions jumped dramatically in ways that other similar positions, offensive and defensive coordinators in the NFL, NCAA Division I head coaches, did not, because in contexts where they did not use the Rooney Rule. So that's sort of a dynamic question you could ask. But I want to actually ask a sort of more basic and actually static question, which is, what is the effect of the Rooney Rule on the quality of candidates? Now, what's interesting about this question is that in a world that was free of any kind of bias or disparate impact, you might say, well, the selection I was making was unconstrained optimization. I get to choose any set of k. Now you've asked me to engage in constrained optimization. You would like me to choose only among the sets of k that have at least one element that intersect, x in a non-empty way. And constrained optimization can't beat unconstrained optimization because I'm simply optimizing the same function over a smaller feasible region. But the question is, like, could there be something else to this story? We know when you're dealing with people who have behavioral biases that sometimes limiting their freedom of action can actually improve their performance, right? So we know, for example, that to take a completely different example, if you're teaching a large undergraduate class and you plan to assign 6 homework assignments, you could make one due every 2 weeks, or you could say, I have all of these 6 assignments ready at the beginning of the semester. I'm going to give them all out at the beginning, and I'll say, you're all grown-ups, do these 6 over the course of the semester, pace yourselves, and I want them all done by week 12. And as anyone who's ever taught a class knows, option 2 turns into an unmitigated disaster because students get to the final week of class and they're too far behind. You have these emergencies. And so instead, you constrain their behavior. You force them to engage in constrained optimization, and in that way, in fact, improve their performance. Maybe, given that this too, we're talking about bias, could something similar be going on? And that was what Manish Raghava and I were intrigued by, that could this be a similar case where we can actually improve performance, right? So it's not simply that we're addressing this manifest disparity by including members of group X. Even in simply a pure maximization sense, we're improving the objective function. And we'll see that, in fact, for sort of a natural set of assumptions, in a sense, there's a range of parameters where we are. So let me tell you how that works by describing a very simple model. And our goal that Manish and I have is to make the model as simple as possible. And despite that, it's going to actually end up leading to a fair amount of complexity. Okay, so ingredients of the model. Basically, applicants, a population with 2 groups, X and Y, and a decision maker who is ranking them. So first, applicants. So let's imagine each applicant has some single, and again, this model is intentionally reductive because we sort of want to see this effect as cleanly as possible in the sense of the model. So there's many moving parts that we could add to it. That's clear. But so in this reductive model, every candidate has a single numerical feature of interest. Okay, and we see these values, let's assume exactly. So Z1, Z2, and so forth from the candidates. And each Zi comes from a power law distribution where the probability that Zi exceeds some number T is like T to the minus some power. Why is this? Well, because I'm in places where we're applying the Rooney Rule. We're hiring head coaches, we're hiring professors, we're hiring executives, we're signing on musical artists. These are effectively creative professions where there's an enormous empirical literature now arguing that total output in creative professions is governed by things that are approximated by power law distributions, right? So the lifetime citation count to an academic, the number of views that a YouTuber acquires, the number of song listens that a musical artist acquires, the amount of revenue generated by a sort of high-level salesperson. These all follow these heavy-tail distributions. And the key thing for us about power laws is that large values are surprisingly common, right? That these are fields dominated by sort of superstars, by outliers, in an actual quantitative sense, right? That there are some people with just enormous numbers of views on YouTube, some people with enormous citation counts, and it follows this heavy tail distribution. Okay, the decision maker's objective is to choose, again, a list of K, and we're gonna say they're choosing to simply maximize the sum of their Zi values, right? So this is a natural fit if I'm trying to say I'm gonna give out an award to K people, I'm gonna hire K people. The Rooney Rule originally was conceived of as step 1 in a 2-phase process. I invite K people to interview, then I interview them, I pick one. That's a more complicated thing that we're not trying to model here. We're just modeling a one-shot decision. Okay, now, this is a particularly easy function to optimize, obviously, because I just picked the top K, that maximizes the sum. Now, let's imagine that the decision maker can only make ordinal comparisons, okay? So when they see Zi and Zj, they can decide which is bigger, but they don't have direct access to the values. And again, this is simply a model of, say, sort of a person who's able to look and make these evaluations, or some algorithm that's not able to compute these exactly. Okay, so they have indirect access to Zi. That's sufficient to maximize this function because with ordinal comparisons, I simply sort, I take the top K. Okay, next, we'd like to have biased evaluation across groups. So I have group X and group Y. And let's say that I have n people from group Y, and I have alpha n from group X. Right? So, and X is the group where there's bias against. We could think of alpha as a fraction less than 1, but that's actually not going to be crucial for us. But if you want, you could imagine that. Okay, the decision maker engages in an extremely simple form of bias, because again, in this part, I'm really treating the bias in the decision as a sort of just a black box atomic step. So again, in our reductive simple model, they evaluate each Y candidate perfectly. When they see a Y candidate with potential Yi, they evaluate as Y. When they see an X candidate, their bias beta kicks in. They estimate the potential not as the correct answer Xi, but as Xi over beta. Okay, and then they make ordinal comparisons. So now you see the challenge a decision maker like this is facing. They want to sort everyone because they do want to maximize this objective, but they can't control for this bias. And so if they attempt to sort, then in the schematic diagram here, the X candidates get sorted into the list multiplied down by 1 over beta. And so when I see that these top 2 people are blue, for example, is that because they truly are the top 2, or because this red candidate here, who's in 3rd place, got shifted below them because of the bias? And in a sense, at the level of ordinal comparisons, there's no way to know, right? I can only make guesses about that. So this is where we see that the Rooney rule might actually start to improve the objective function, because your bias, which you can't control or don't want to control, is shifting these X candidates downward. By forcing you to take at least one, it could be that I'm forcing you to take someone who should have been in the top K and isn't, okay? So is that actually going to work out? So the theorem that Manish and I were able to prove was a characterization in this model of where in parameter space the Rooney rule actually produces a positive change objective, and to carve out actually a large region of this parameter space where it in fact does. Right. So again, this decision problem is characterized by 3 numbers: alpha, the composition of the pool, what fraction are from group X; beta, the level of bias, right, by what number greater than 1 are the X values being divided down; and delta, which is the power law exponent, which think of it as qualitative as like how abundant are outliers and how extreme are the outliers, right? How far into the tail. As delta goes to 0, we see just increasingly extreme outliers who dominate everybody else, right? Okay, so we're in this 3D parameter space, right? Alpha, composition of the pool, X versus Y, beta, level of bias, delta, the power law tail. And what our theorem does is basically carves up this parameter space into 2 regions, the region where the Rooney rule helps and the region where it actually hurts, and to show that both regions are in fact non-empty in this model, okay? The theorem essentially, this won't add much to the picture, but right, that there's an explicit function, so the Rooney rule produces improves utility and expectation for sufficiently large number of candidates if and only if this function is greater than 1. The functions, even though we sort of worked hard to keep everything as simple as possible, like, I mean, we dialed down all the decisions down to minimum complexity, even for k equals 2, this is the function. I put it up not to actually parse the function, but just to show you that it has sort of some amount of typographical complexity. It's actually easier to look at it in the parameter space itself. So here's actually f equals 1. So the vertical axis here is the bias. This axis is the power law exponent, and this axis is the composition of the pool. And so the vertical axis says, when I'm above this curve, beta is large enough that the Rooney rule is producing an improvement. By constraining my behavior, I'm forcing myself to make better choices. When I'm below this surface, the Rooney rule is hurting. Okay, and you can see in some ways it behaves as expected. So as alpha gets smaller and smaller, fewer and fewer of the pool, and again, this is k equals 2. I'm trying to choose 2 people, and if I'm choosing 2 people, should I reserve 1 slot for group X? As alpha gets smaller and smaller, the bias needs to be higher and higher to justify the Rooney rule, and it rises toward this cliff, basically, where it diverges to infinity. There are some choices of alpha and delta where essentially no amount of bias justifies reserving 1 slot for group X if group X is too tiny of a fraction pool. In this direction, it says as the power law exponent gets smaller, the tail gets heavier, and things diverge in a different way. They're also, and again, from such a simple model, we don't understand why there were these weird non-monotonnicities, which suggests something interesting going on. But I want to tell you just one thing about sort of how this theorem is proved. The full version involves working out order statistics for power laws, a lot of which was actually not very well understood, which is interesting because ranking of people who come from power law distributions, if you think about it, it's sort of a very natural activity, and yet it's hard to work with order statistics of power laws. So let me tell you one little glimpse from the proof, which I actually found interesting because it actually, in a sense, taught me something about bias just from the model that I really feel like I hadn't fully understood before then. So I want to just walk you through that. So let's ask the following question. Let's assume a world of infinite bias, and ask for which alpha delta pairs, composition of pool, power law exponent, does the Rooney rule improve utility in a world of infinite bias with two candidates? Right now, we don't typically live in a world of infinite bias, but you can imagine this is, infinite bias could correspond to, I'm doing admissions for my graduate program, and we simply ignore all applications from country X because we simply don't understand their educational system. And so I could be missing somebody who's essentially arbitrarily good because we just don't attempt to read those applications, right? That would be a world of infinite bias. Here's a surprising fact. 2 slots. No matter how small the fraction of X candidates, there is a small enough power law exponent so that the Rooney rule improves utility if you impose it. Okay, let's think about that. That's saying, right? That's saying X could be a 5% portion of your pool. You're reserving 2 slots, that's it. And yet there's a small enough power law exponent so that it would be expectation improving to reserve a slot. Now, we could do the math, and I won't run through it in detail, but effectively, without the Rooney rule, in a world of infinite bias, the second candidate, you'll always pick the top Y candidate. Without the Rooney rule, the other candidate will be the second X candidate, the second Y candidate. And if the Z star is the expected value of the top Y candidate, it turns out delta over 1 plus delta is the functional form for the second one. And that comes from order statistics. With the Rooney rule, the other candidate will be the top X candidates. There, we need to sort of work out some new bounds, but the expected value is complicated, but it's asymptotically this alpha to the 1 over 1 plus delta. And now we just compare these two, and we discover that for every alpha, there's a delta small enough that it gets below alpha. Okay, but we wrote this down, and then for the next few days, we're like, this theorem has to be wrong, because here's a simple, what we thought, argument why this theorem somehow has to be wrong, because, or this fact. Consider that X is 20% of the population, okay? Let's say group Y, and let's arbitrarily break it into groups A and B. We're just gonna pick the 80% who comes from group Y, who's all indistinguishable to us, we just get their Y values. And we're gonna say, this half is called A, this half is called B. Well, then I've identified 2 groups, A and B, who are each twice as large as X. So group A is 40% of the population, and they all come from some power law distribution. Group X is 20%, and they come from some power law distribution. Now, it's the case that the expected max in group A is higher than the expected max in group X. That's just a fact. It's twice as big. They're coming from the same distribution, so the max is going to be higher in expectation in group A. The same is true in group B. So I have just named 2 people, the max in group A and the max in group B, who are both higher than the max in group X. Yet you're telling me that I should reserve a slot for group X, one of my 2 slots. How is that possible? And the answer is, the theorem is right. And it's this intuitive argument that's actually wrong. Because here's what's going on. It's not that I'm being forced to choose one of the top in A or the top in B. I'm choosing the better of the 2. The argument is actually about the second best of these 2 or this one, right? It's the second best in the group of 80% or the best in the group of 20%. And what it comes down to is that power law tails are so heavy, right? There's so much mass in the outliers in a power law that the best in a group of 20% of the population in expectation will be better than the second best in a group of 80% of the population. And in the end, that's actually what we're losing when we engage in bias in these kinds of decision making. That by not paying sufficient attention to this particular group of 20%, we're missing someone who's potentially stratospheric in their performance, right? Where the power law has pushed them out so far that by missing them and by going for the second best person in the group that we do understand, group Y, we're actually doing worse in expectation. And the sort of more extreme the power law is, the smaller X can be, and that will still be true. Okay? And so that, in a sense, is sort of what we ultimately sort of truly learned from this abstract model of decision making. A bunch of other technical things that I'm going to jump over here to get onto the second part. But so just a few things, right? So this was a very simple model where the decision making was essentially black box. The bias was a black box assumption of bias. We didn't really get into the decision making. That's what I want to get to next. We had indirect access to numerical values. there's a lot of potential extensions to the model, and actually in the past year, a number of lines of work have sort of developed alternate models, and some of them extensions of our model, some of them other variations. For example, we made assumptions about power laws. We made assumptions that the form of the bias was multiplicative. There's a lot of interesting questions you could say about, obviously, noise in the evaluation of the candidates. In a sense, this perfect evaluation of candidates made for sort of an interesting sort of theoretical punchline here, but obviously noise in the evaluation is going to be a big question. And obviously, oh, go ahead. Yeah.
Quick question, clarification question from the audience.
Yes.
Can you remind again how the candidates from each group are selected? Are they random draws or top ranked?
Oh yeah. So in each group, they're top ranked. And again, because we're essentially trying to make sort of the minimal assumptions that we, and this noise in the evaluation of candidates is sort of on the way to that, right? So as I add noise, I basically sort of continuously morph from perfect evaluation top candidates to random evaluation in the limit of infinite noise. And essentially this more recent work kind of tries to look at, can I sort of look at that continuum as I go between them? But yeah, that's a very good question. Okay, and obviously there's a long history of work about, in all these decision processes, the choices the candidates make about investing effort, and we're not talking about anything there, right? This is really sort of, I would argue, making a point about a simple way to see the cost of introducing bias into even a small fraction of the population in a world where the top candidates have enormously high values, as they do in many of the domains that we were talking about. Okay, but I want to get to this sort of next part of it, because as I said, in the first part, we want to talk about the decision is really a black box, and the bias is just this black box scaling down of values. But I want to think about the actual implementation of these decision rules, and how decisions we make in the implementation to have more complexity or more simplicity, for example, can actually play a role in what, or can create channels by which bias can make its way into the decision. And that's what I'm talking about here. And this will ultimately also build up to a kind of intervention, an intervention different from the Rooney Rule, but an opportunity that's sort of easy to miss if you're sort of not thinking about these issues. We can think about the models I'll talk about, certainly as models of algorithms. I mean, I'll be talking in terms of feature vectors, functions of feature vectors, and the sort of choice to keep or project out certain coordinates of the feature vectors. And that's very much an algorithmic kind of question that we would see straight in the machine learning pipeline. Slightly more metaphorically, we could think of these as models of human decision-making in a very abstract sense. And we'll see that actually decisions we make about simplifying algorithms seem to connect in interesting ways to models of human stereotype formation, right? This principle that if we're in the presence of low information or limited available time, that's when we're particularly prone to fall back on stereotypes. All right, let me make all of this concrete. So here's, right, so I'm gonna need a new model from the one I had before, because I don't want these decisions to be just black box decisions or atomic decisions. I want to actually look at the features. So I'm gonna say applicants now are actually described by a feature vector, a k-dimensional vector of variables x1 to xk. And let's see, these are Boolean variables. And there's a productivity function that I'm going to use. That's basically says, if I knew, the full feature vector, that would describe everything I need that's relevant to selecting this person, and f would tell me the value of this person. Right, and again, you can keep a running example in your mind, like hiring or PhD admissions, right? And we're in this abstract world where there's some function f, where if only I truly knew x, I truly knew f, I could compute it. And my plan is to, again, sort by the f value. This is the same as the first part of the talk, and I'm going to admit some fraction of the applicants, the top R fraction. Okay, so I'm concerned about disparity between two groups, and these two groups I'll think of as an advantaged group and a disadvantaged group. And to emphasize this advantage versus disadvantaged, I'll rename them to A and D, A for advantage, D for disadvantage. Now, the key point is this productivity function f is a function of the features, and f doesn't care what group you come from, right? So if I create an extended feature vector x comma A or x comma D recording your group membership, f of xa equals f of xd equals f of x. And the decision maker is ranking by f. Okay, so in that sense, the decision maker wants to just maximize f. So if this is true, in what sense is there disadvantage? There's disadvantage in the distribution of feature vectors. In group A, it's easier to acquire beneficial feature vectors, right? So In particular, the condition I'll use here is a likelihood ratio condition, although I'll come back to the question of what assumptions we should really make here. If X is a better feature of X than X prime, it confers higher productivity, then it is more overrepresented in group A relative to group D. Okay, so good feature vectors are easier to come by if you're in group A. And my decision maker effectively is an F maximizer. They're trying to maximize F. They're not biased in that they're not interested in group membership, but they're sort of lazy about disadvantage in the sense that they're not particularly interested in correcting for disadvantage either. They simply want to maximize F, and if that leads to them admitting arbitrarily more people from group A, then that's what they do. Okay, and that's sort of right. And it's the sort of indifference to disadvantage that we're going to see is part of where bias is going to start coming. Okay, let me make all this concrete with a very simple example. An example small enough that we can work it out in our heads, although of course, a lot of this is going to, in reality, apply to more complicated functions. Let's imagine we just have two Boolean variables. The true criterion is the conjunction of x1, x2, right? And so if x1 equals x2 equals 1, f equals 1. Half the population is from group A, half is from group D. Applicants from group A have xi set equal to 1 independently with probability 2/3 for each of the two coordinates. Applicants from group D, reflecting the disadvantage, have xi set equal to 1 with only probability 1/3. And so everything is summed up in this truth table here. Right, the values and also the fraction of the population. Now, so what's going to happen? So the decision maker, if they had perfect knowledge of F or perfect knowledge of x1, x2, it could perfectly calculate F, would just rank. And 5/18 of the population has F equal to 1. So at all admission rates are up to 5/18, all the admitted applicants have F value 1, which is the best possible. And I'm pulling indistinguishably from the people with F equal to 1. And between A and D, they're in a 4-to-1 ratio. So there's a 1/5 fraction from group D. Okay. And so that's reflecting the disadvantage, right? The disadvantage in group D is now being reflected in the low rate of admission. Okay. Now, suppose we decide to simplify F, and this is sort of the starting point for what I'll be talking about, because essentially much of the machine learning pipeline on functions infinitely more complicated than this one that we're working out by hand consists of controlled simplification of the function, right? And one simple way to do that is to project out some of the variables. Why might we do that? Well, maybe collecting x2 is just too expensive, right? Maybe if this is graduate admissions and this is an extremely stylized example, x1 is the applicant's grades and x2 is the quality of research that they did as an undergrad. And it's very easy to look at grades and they're just numbers. It's harder to actually go look at someone's paper and decide if you think it's good research, okay? And so it's just too expensive to collect x2 realistically. Maybe if we had a model much more complicated than this one, we're aiming for sort of interpretability of the model. We can interpret the model if it's only using a small number of features, so we're gonna decide to simplify by throwing some out. We might even be doing it for reasons of out-of-sample generalization, right? So one principle of regularization is that, under some reasonable assumptions, simple models are going to generalize better to held out data, to unseen data, than complex models. And so there's actually something in here that creates, as you'll see in a few slides, the intriguing suggestion that, regularization might sometimes actually interact in complicated ways with bias and how it can enter the system. For all these reasons, we might simplify by projecting out x2. And what happens when we do that? I'll continue with this example, because as it turns out, simple though this example contains a lot of the complexity that I'll then sort of state as a general theorem for arbitrary Boolean functions. Okay, so simplification, if I project out x2, I go from this 8-line truth table to this 2-line truth table, where either x1 equals 1 or x1 equals 0. And I start by pulling indistinguishably from row 1, and then I move on to row 2 once I've exhausted row 1. Right, so this is an F approximator, it collapses rows. So now at all small admission rates, the average F value that I'm getting is 5/9, not 1, because I've lost information. But the fraction from group D is 1/3, not 1/5, right? So relative to the true F, I have gains in equity, more people come from group D, losses in efficiency, F is lower. And that's a trade-off that we often see. But there are also two more subtle things that happen here, even in this simple example that I wanted to highlight. One is just a straight difficulty. The other is sort of a potential missed opportunity and a chance for a kind of intervention, as I was suggesting, that will sort of make sense once we see what's going on. Okay, so the first potential difficulty is the following. Recall this decision maker is an F maximizer. They just want to get large values of F. They don't care about the value group membership. They're not seeking it out because they just don't plan to use it. They're not particularly concerned about the fact that a small fraction of their accepted applicants come from group D, but right, so they're not trying to correct it, but they're not trying to seek out group membership either. If you ask them, they'd say, I don't care about it. Now suppose we went to the reduced truth table and ask, do you care, would you like to know the value of group membership? Right? With the 8-line truth table, they would have said, no, I don't care. Now they'd say, well, in fact, yes, I actually would like to know the value of group membership. Why is that? Because if I knew the value of group membership, I could take my 2-line truth table and I could unsimplify it into this 4-line truth table where I sort by X1 and by A, right? And now if I put the first row first, second row second, A, and as we know from the sort of principles of statistical discrimination, A is giving me conditional information about the variable that I'd like to have, but don't, namely X2. And so this would now be a decision rule I could use, which produces a higher value for F for every, for every admission rate, it's always at least as good and often strictly higher. So essentially, simplification transforms disadvantage into bias. Before we projected out X2, there was disadvantage. There wasn't bias in the sense that the decision maker didn't care about the value of group membership. Once we simplified, that disadvantage now is manifested as bias. And this is the sense in which I was arguing earlier that some of these models allow us to sort of also think, somewhat metaphorically about human stereotype formation, right? That in conditions where we're lacking information, we might fall back on stereotypes. We also see this, for example, in empirical work on things like beyond the box policies in hiring, where laws that say that, we've decided there are certain questions you should not be allowed to ask on job applications because they perpetuate disadvantage. And then this, extremely creative work by people like Amanda Egg and Sonia Starr, looking at the fact that sometimes in resume audit studies, places where you've introduced beyond the box policies, you can see an increased disparity in callback rates, with one hypothesized mechanism being that when you've denied people certain kinds of information, you sort of increase their tendency to fall back on stereotypes in outright pernicious ways. And so we think of all these as very human things to do, this idea that we're going to fall back on our stereotypes. But what we're seeing here is that even an 8-line truth table will fall back on stereotypes if you instruct it to care about F and you withhold relevant information from it. So that's the first point. The second point is that the simplification that we're doing is not even the best trade-off you can find between efficiency and equity. In a kind of economic language, if I think about sort of the two-dimensional space of efficiency and equity of my decision rule, simplified rules are not on the Pareto frontier of efficiency and equity. They can be simultaneously improved on in both dimensions. They're not the optimal trade-off. And how does that work? Let's do it in the example, and then that'll sort of balloon back into a general definition. Go back to my two-line truth table. Here's a kind of strategic unsimplification I could do to that. I could go into the first row and I could sculpt out a subcell from it, which is X1 and X2 are both equal to 1. Group membership is D. And I put that row first. And again, I admit, first row till I've exhausted it, then move on to the second row, then move on to the third row. And now if you think about it, I'm admitting all of this group that had average value 5/9, but I'm admitting them in a graded order, where I'm admitting a subset with F equal to 1 first. And so for every admission rate, I'm doing at least as well in efficiency and often strictly better. And I'm certainly doing at least as well and often strictly better on equity because I'm admitting people from group D first. Right? And so I have a simultaneous improvement in efficiency equity by a kind of controlled unsimplification. This too, to continue my graduate admissions story, is something that we might recognize from our experience, say, with graduate admissions programs, right? We might say, as a graduate admissions committee, we don't have nearly enough people in our entering classes from group D. What can we do about this? One thing we could do would be to create a summer program where we invite people from group D to come do research with us over the summer as undergraduates. And they do this research with us. And then the ones who do extremely good research, we keep track of that, a year later in our PhD admissions process. What have we done? We've pulled out an extra row. And we've said, for some people from group D, those where this expensive variable X2 is good, we've spent the effort to collect it. And what we now have is a group of applicants who are actually better than the average applicant we're admitting, and from group D. Right? We've improved F, and we've also improved equity. Right? And when we do that, we're essentially doing a version of this kind of truth table operation. Right? We're finding a creative way to do that. So what it says is that, in the space of truth tables, right, on this landscape of all possible simplifications of the function F, when we simplify in a kind of crude way by just projecting out variables, we get to a kind of unstable point on the landscape. in one direction, we can tilt toward incentivized bias, where the decision maker is, develops this pernicious incentive to seek out group membership in ways that they didn't before. And the other direction, we can move in the direction of Pareto improvement, unsimplifying so as to simultaneously improve in both efficiency and equity. And the basic result that Sendel and I proved was that what holds in this example holds for every Boolean function. Okay, so for every Boolean function f with real valued outputs, satisfying the disadvantage condition I stated, and a genericity assumption that I haven't stated here, which essentially says that the values of f are in some kind of a general position. And for every simplification of it, by collapsing rows of the truth table into cells and using average values, then two things hold. One, Pareto improvement. There's always an f approximator that strictly improves on G in both efficiency and equity, right? So it can always be unsimplified in some strategic way. And two, incentivized bias. If G does not use group membership, then adding group membership as a variable increases efficiency and reduces equity. So by increasing efficiency, we create an incentive for the decision maker to seek out group membership. And it's a pernicious incentive because it's going to reduce equity. Now, I can't say much about how this theorem is proved, and I only have a couple minutes left. So I just want to show two slides on sort of the main subtlety that comes up in proving this, and then I'll wrap up with some conclusions. So the subtlety that comes up is actually best seen, as often is the case when you're trying to sort of expose the subtlety in the proof of a theorem, is to relax one of the assumptions and see where things break as a kind of guide to this. So let's say I took the likelihood ratio condition, which is admittedly a very strong condition on distributional comparison, and I relaxed it to simply a distribution in means. Okay, so rather than say, this ratio condition, the mean value of f in group A is higher than the mean value in group D. That's implied by likelihood ratio, but doesn't imply it. Okay, what actually happens now? Well, now the theorem as stated does not hold. We need a weaker version of the conclusions. And it's instructive to see why it doesn't hold. It doesn't hold because of examples like this. And I don't expect you to, this example also is only 8 lines long, but it's not something you can really work out in your heads in real time. I'll tell you the key thing about this example. If I project out x, so D has a lower average here, lower average value of f. But if I project out x2, I get this truth table. In this truth table, the decision maker develops an incentive to seek out group membership, but they have an incentive to seek it out so as to help group D, the disadvantaged group. Because when x1 is equal to 1, the average value of group D is higher. And when x1 equals 0, the average value of group D is also higher. Right? So it's kind of weird because group D has a lower overall average, yet conditional on any choice of value for x1, it has a higher conditional average. It sort of initially feels like that can't happen. The fact that it can happen is called Simpson's paradox in statistics. This is sort of the pure form of Simpson's paradox. That I can, and essentially for our purposes, it says that there's a simplified rule, even with a difference in means, where in fact the incentive actually goes in the reverse direction. So we have to weaken the conclusions of our theorem with a difference in means, and there's interesting open questions there. But for likelihood ratio, essentially it says the technical crux of what we're doing is to prove what you might call an anti-Simpson result, okay? And that basically says if we assume the likelihood ratio condition, then in a sense, that's strong enough that it smooths out everything such that Simpson's paradox can't happen. That if I have likelihood ratio in any way of partitioning the feature vectors for A and D into cells, there's at least one feature vector whose estimated value in group A is higher than in group D. And that one feature vector, which is sort of the crux is to prove that existence result, becomes the handhold by which we can create Pareto improvement and we can sort of create incentives for incentivized bias. Okay. All right, and again, that's just a sort of glimpse of like what the main thing the proof has to deal with. With that, I'll wrap up. And so, this part has been about simplification and some of the surprising things that it can do, and it's been down at the level of the implementation of the decision rule. But if I pop back up to sort of the two parts taken together, the full machine learning pipeline leading to decisions, there are a lot of interesting questions that we can think about here. One, just to mention in this bullet here, is that everything I've been saying so far has actually been about evaluating individuals. It's been saying if I would like to hire K people, I evaluate K people individually and I rank them and I take them. But there's a long line of work on the performance benefits of diversity in teams, work by people like Scott Page, for example, who was certainly a pioneer in thinking about this theoretically, that says I should really think about a selection of K people for any purpose like employment, graduate admissions, whatever, as a set function, right? This is a set. This is a function of the set that I'm choosing, and there are certain complementarities and synergies that I can actually benefit from in ways that simply selecting the k highest people on some unidimensional scale might not achieve. And so in some ongoing work, we've also been thinking about these kinds of questions. More broadly, I think what's interesting is the way in which algorithms bring them into these kinds of settings. It isn't just a quantitative change, but there's been a qualitative change also, that it creates, it allows and even requires a kind of concrete, explicit discussion about objective functions and about the use of features, the use of data in these kinds of decisions. That's going to force us to sort of grapple with certain issues, not just when we try to automate them, but even when we try to engage with them as humans. And I think many fields are going to have to play a role in setting these priorities. Computing, applied math, operations research, the mathematical social sciences and statistics, together, with the empirical social sciences, with law and policy. And I think, there's an opportunity for, I think, all of us to engage in what's going to be a very, very interesting direction going forward. Thanks very much.
Thank you, John, for a very nice and inspiring talk. We have time for some questions, and I will just start reading some of the questions that are in the chat. And let me also remind the rest of the audience, if you have questions, please type them into chat. And let me relay the first question from Jaiha. In the studies, I guess this is about the first part of the talk. In the studies of the Rooney Rule and stereotype formations, do the results require assuming that the performance metrics are distributed in population independent of the protected characteristic?
Yeah, so we're assuming that people are drawn independently from this distribution, and it's a single it's a single distribution across the population. And that assumption, in some sense, is one of the things that gets morphed as we go into the second part of the talk, which is to say one way in which disadvantage is manifesting itself is that acquiring beneficial feature vectors may be more costly or more difficult if you're coming from one group than others, and so that then begins to play a role in this also. Yeah.
And there's another question from an anonymous attendee. How does this reconcile with the HBR results from 2016? That if there is only one applicant from a disadvantaged group in your pool of applicants, they will never get picked. I assume this is
right.
The second part of the talk.
Yeah. This is also about the Rooney Rule. Yeah, so this is, of course, a criticism of the Rooney Rule, and one reason why, for example, in the National Football League, it was initially effective and has begun to seem to attenuate over time has been and part of it is these kinds of principles. I mean, so of course the short answer to that is that there isn't anything in our abstract model that says that people are going to take into account like how many of people from this group are in there. I will say this is yet another example of this principle on this bullet point I have here on the final slide, that many of these things are best thought of as set functions rather than as individual functions, right? That, part of the challenge is that if I'm thinking about how I select a set of K, I'm probably not doing a kind of in isolation ranking of items and then just sorting, but rather I'm thinking about the full choice set. I'm thinking about like, this would be the set of K I'm choosing, or this is the set of K, the context in which I'm evaluating. And so I think bringing these choice set effects into these models is going to be increasingly important. And we're seeing an increasingly sort of strong line of research in machine learning and computing on sort of dealing seriously with these kinds of choice set effects. I'll also say that actually the model, one direction which the model does extend quite naturally is that, the Rooney Rule as specified said, have at least, one member of group X. But, there's a kind of, Lth order Rooney Rule, which says have the number of members from group X be equal to L, where L could be 1, it could be 2, it could be an arbitrary number. We can do similar analyses with that. And, and in some sense, even within the simple model that we've defined, one question is, what is the actual optimal choice of L? There's no reason why it should be 1. So that's certainly one concrete question. But I think the question that this more gets at is we should really be thinking of, in many of these cases of these things as set functions rather than functions of individual variables. And I think there's a lot of interesting work there to be done.
Perfect. So I remember there was someone who raised a hand during the talk. If you still have a question, please raise your hand. And in the meantime, I have a quick question. So I found this insight about how simplification transforms this disadvantage to bias quite interesting and striking. intuitively, I would expect a similar conclusion to hold for any coarsening of information, not for the particular way we simplify the table in your example.
Yeah.
Is that accurate?
Yeah, so in the paper, we actually sort of start with the Boolean function framework, but then we end up sort of setting this in a more general framework where it's essentially, say applicants can be from one of n types. And then I say I'm simply going to, as you said, coarsen the types by creating a non-trivial partition of the types and using the average value across that. And for essentially a very wide family of sort of partitions of types, using approximation by averages, we get a similar sort of result. So yeah, so it's really less a property of projecting out variables from this multidimensional model and more if I have types and I group them by partitioning.
A related question that your example made me think of is the following. So if I'm, for instance, dropping one of the columns, let's say x2, if it is the case that the candidates could, let's say, invest some effort and improve some of their features, I'm taking away that incentive as well. In some cases, may be hurtful. Any thoughts on that?
Yes. Yeah. So there's a lot of interesting questions in how sort of things are happening on the decision maker side or interacting with things happening on the, say, applicant side, to keep the language of applicants and selectors. And actually, following this work, a thing that Manish and I have been thinking about a lot, sort of more recently, is to try to build models of the ways in which different decision rules can create incentives for applicants to optimize one set of features versus another set of features. And there effectively becomes this game played by the selector and the applicant, where the selector has to choose a decision rule, the applicant has to then optimize their characteristics. And the person creating the decision rule, you could imagine that I create one decision rule and it says, you have to achieve a certain thing, and you do that by gaming the classifier. You acquire it in a way that doesn't actually either improve you, or improve your value as an employee. I could create a decision rule in a different way. Like I say, you have to do well, in this course. And the way you do that is by studying and learning the material. And then, yes, you improve that feature, but it wasn't by what we might think of as gaming. It's that you genuinely sort of improved your value as a, sort of future sort of, employee, or you enrich yourself. So, and this obviously has sort of deep connections to the literature on principal agent problems in economic theory, where the principal is trying to incentivize an agent to do things, even though the principal can't directly measure the agent's effort. And it does feel like there's this connection that we've begun exploring in this kind of work between sort of the way we set up admission or selection rules and the kind of principal agent models that we've been seeing.
Very nice. Thank you. Thank you, John. I think we are out of time, and I believe all questions are also